Solution dilution. Sounds like the beginning of a song or a poem or something. We use a lot of chemicals in the lab, and those chemicals, many of them are solids in their pure form, but we tend to do a lot of reactions that occur in aqueous solution. And so it's often convenient to make up solutions of the chemicals we're going to be needing and store them in a more concentrated form and dilute them as needed. It's a little bit like buying frozen concentrated orange juice at the grocery store, right? It takes up less space, it's just more convenient. So when we have these concentrated stock solutions, we keep them in stock in the stock room, that's why they're called stock solutions. We have to dilute them just like you would dilute the concentrated orange juice before you drink it. So to lower the concentration, we're going to add solvent. Generally, that solvent is water. When you add water to a solution, when you add more solvent, it does not change the amount of solvent present, right? If you have a solution of sodium chloride that's 1 mole per liter of sodium chloride, and you add some more water to it, the amount of sodium chloride in there is the same. You've just changed the volume, and so you've decreased the concentration. It's like when you dilute that orange juice. You get that little can of orange goodness, right? And you pour it into a pitcher, and you look at it, and it's all in there, and then you add 3 cans of water to it. You still have the same amount of orange goodness in there, but the volume has changed. Does that make sense? So we've got this handy little equation, M1V1 equals M2V2, which is what we use when we're doing calculations involving dilution. The molarity of the first solution times the volume of the first solution is equal to the molarity of the second times the volume of the second solution. Yes. So molarity has units of moles per liter, and we're multiplying by volume, usually in liters. And so the liters cancel out, and that gives us moles of solute. On the right side, we also have molarity, moles per liter times volume in liters, and that also gives us moles. This equation works because the moles of solute are not changing. We're just changing the volume. So here's an illustration of making a solution using dilution. So here we've got a 10 molar solution, and we're going to use 0.150 liters of that 10 molar solution. So we're going to put that into our flask, and then we're going to add more water until we have a total volume of 3 liters. So if we look at the moles of solute that we're adding initially, 0.15 liters times 10 molar. So that's written out down here. That's 1.5 moles of solute. And over here, after adding the water, we've got 3 liters of solution, and the concentration now is 0.5 molar. And if you take 0.5 moles per liter times 3 liters, you also get 1.50 moles. So we measure out the concentrated solution. We put it in a bottle, a flask, just like you're pouring that orange juice concentrate into a pitcher, and then you add water, and then you need to mix it up, right? Because if you just pour water in there and then try to drink it, it'll be all really watery at the top and just all gooey at the bottom, right? We have to mix it. So in this flask, we also have to mix it. So let's practice using that equation. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? Well, we've got some numbers here. Let's pull them out and write them down. So we have 100.0 milliliters. We have 5.00 capital M. We have 0.750, capital M. The capital M stands for molar, moles per liter. It's very convenient when we're typing on the computer, but when you're writing with your hand, write moles over liters. The capital M does not stand for moles. So what I'm going to do is I'm going to get rid of that capital M, and I'm going to write what it's standing in for. It's standing in for moles per liter. And don't write it as a horizontal fraction. Don't write it like this, because then your brain doesn't recognize that liters in the denominator. And I saw this happen several times on the exam, where students did a calculation and they had their units like this, and then you put the units together wrong and got the answer wrong. So don't do that. It's not wrong, but it's confusing and can lead to wrong answers. So we are diluting, right? We even have the word dilute in the question. So we're going to use our dilution equation, M1 V1 equals M2 V2. So we're looking for 2 volumes and 2 molarities. And the units are going to tell us whether these are volumes or molarities. So here, this is milliliters. That must be a volume. And both of these have units of moles per liter, so those are molarity. Now we have to assign them 1 or 2. There's no initial and final. There's no concentrated and dilute. It's just 1 and 2. It doesn't matter how you assign them, you just have to get them paired up correctly. So this volume, which of the concentrations does it go with? It goes with the 5, right? It says 100 milliliters of 5 molar. Those two go together. I'm going to call them both 1, M1 and V1. So M1, V1 and M1. That makes my other molarity 2, just molarity of the other solution. And what am I trying to find? I'm trying to find the volume of that other solution. So I'm looking for V2. And I'm going to get rid of this. It specifically asks for milliliters. Well, we've got our equation. M1 V1 equals M2 V2. And I'm trying to solve for V2, so I need to rearrange my equation. So if I divide both sides by M2, M2 will cancel out on this side, leaving me V2 by itself. Yes. So V2 is M1 V1 over M2. Now I'm going to put my numbers in. So molarity 1 is 5.00 moles over liters. And volume 1 is 100.0 milliliters. And that's divided by molarity 2, 0.750 moles over liters. Do I have to convert milliliters to liters to do this problem? I don't. Because the units on this molarity and the units on that molarity are going to cancel out. I've got moles per liter in the numerator and moles per liter in the denominator, and so those will cancel out, leaving me just milliliters, which is a unit of volume, and is actually the requested unit of volume. So now I'm going to take my calculator, and I've got 5 times 100 divided by 0.750, And I get a lot of 6s. My calculator is showing me 666.666. Right? It's ridiculous. How many significant figures should that result have? 3. My molarities both had 3 significant figures. This volume had 4 significant figures. But we're going with the smallest. So we're going to round this to 3 significant figures. And so I'm going to say that the volume 2 is equal to 667 milliliters. Any questions? So dilution problems can use this equation. Typically, they'll give you 3 values and ask you to find the 4th. Occasionally, we'll mess with you and make it a little more difficult, but it all comes down to unit conversions in addition to M1V1. So molarity is a great unit for chemists. It relates moles of solute to liters of solution, and so it's very useful for converting between amounts of reactants and products in a chemical reaction. So our general mantra for stoichiometry was grams to moles to grams. And that's still a good starting point. But sometimes we need to change up the ends. So here, when we're using a solution and we have the concentration in moles per liter, we may start with a volume of that instead of a mass. And then we convert the volume to moles, and then we may need to convert to volume of the desired thing, or we might need to go to grams. So there's lots of variations on the ends. Mole to mole is always going to be in the middle for stoichiometry problems. So let's do an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced equation? So I'm going to take the numbers and write them under the chemical equation because it helps me to organize the numbers. So I've got a molarity for the nitric acid. So that's 0.150. Should I write capital M? Or should I write moles over liters? I should write moles over liters because then my brain says, ooh, that might be a conversion factor. My brain says that. And then it says 35.7 milliliters of blah, 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 sodium carbonate. So I'm going to write 35.7 milliliters of that. And then 0.108 molar sodium carbonate. 0.108, and what units should I write there? Moles over liters. Capital M is an abbreviation for moles over liters. Moles over liter is more useful when we're doing problems because those are the actual units. Okay, so what am I trying to find? Volume of HNO3, right? So question mark, and it wants the volume in milliliters. So I have 2 molarities. I have a volume that I know and a volume that I want. Students are often very tempted to use the dilution equation here. M1V1 equals M2V2. Is this a dilution problem? No, it's not. We're not diluting something. This is a chemical reaction. The dilution equation is not for chemical reactions. If the stoichiometry is exactly right, it will work. And so that's why people sometimes use it, because sometimes it works. But many times it doesn't work. And I know that students like to do that, and so on exams, I intentionally put in problems where it's not going to work. So only use the dilution equation if you're doing a dilution. Here we're doing a chemical reaction. We're going to start with grams to moles to moles to grams. So chemical reaction, stoichiometry, grams to moles to moles to grams. And then I'm going to see if I need to make a variation of that. So this is the thing I'm trying to find out about, and I'm trying to find volume in milliliters. So instead of going to grams here at the end, I want to go to milliliters. And the thing I know about the Na2CO3, I've got a concentration and a volume in milliliters. So this is my starting point, and this is my ending point. I'm also going to start with milliliters. Everybody okay with that?
So basically, instead of grams, it's
Yeah, we're going to use a volume instead of a mass. So I'd like you, I haven't done this much, and now that I'm teaching 1B more often, I'm thinking, I really should introduce you to millimole. I actually have I have 2 stuffed moles in my office. I should have brought them with me. I have mole, and then there's the millimole, and millimole is smaller than the mole. We can use metric prefixes on any unit. You could even use them on inches if you wanted to. And so we can put milli in front of the unit mole, and milli still means 10 to the minus 3. So I want to show you something that makes life much, much simpler. So if I take this 0.108 moles per liter, would that change if I multiplied the top and the bottom by 2? It's still the same relationship, right? Well, why would I do that? I wouldn't, because that's not going to be any help. What if I multiplied the top and bottom by 10 to the minus 3? Still the same relationship, right? What if I use M for milli instead of 10 to the minus 3? This is the same concentration. I'm just using smaller units, and the units are smaller by the same factor. Are you okay with this? Do you see that this is okay? Milli stands for 10 to the minus 3. I think I still have some people that are not sure. If I actually wrote the times 10 to the minus 3 in there, do you see how those could cancel? We can take something in the numerator and something in the denominator. If they're the same, we can cancel them out, right? Well, we don't have to cancel them out. What I'm doing by writing millimoles per milliliter is I am using an abbreviation for 10 to the minus 3. I'm doing it to the top and the bottom the same, and so it's still the same concentration. This gives us the number of moles in millimoles, and it makes things much simpler, because in chemistry, unless you're doing industrial chemistry, we're not measuring our solutions in liters. We're measuring in milliliters, small quantities. We end up with small amounts of moles, and the numbers get a little unwieldy. And so by using milli, the numbers get nicer, and the units work out better. So let's just keep this in mind. What we've got here, we've got milliliters and milliliters. If I go to millimoles and millimoles in the middle, then all those millis are going to take care of themselves, and I don't have to multiply by 10 to the minus 3 and divide by the 10 to the minus 3. Anybody have any questions about that? Okay, so milliliters to millimoles to millimoles to milliliters. So I'm going to start with my volume that was given. 35.7 milliliters. And I do need to write the chemical formula because that's going to change throughout the equation. Next, I'm going to go to millimoles. And I'm going to have milliliters in the denominator. And that's millimoles of sodium carbonate. And then I'm going to go to millimoles. Oh, actually, I can move that over. Millimoles of the nitric acid. And I'm going to want millimoles of sodium carbonate in the denominator. So those are going to cancel out. And then here at the end, I want milliliters of HNO3. And I'll have millimoles of HNO3 in the denominator that's going to cancel out. So I just, I did grams to moles to moles to grams. I switched the ending to, in the beginning, to a volume. And then we made everything milli. Just made everything small. Now I go and put the numbers in. So the mole to mole ratio is the same whether it's moles to moles or millimoles to millimoles. So here I've got 1 mole of sodium carbonate and 2 moles of nitric acid. That's the same as 1 millimole of sodium carbonate and 2 millimoles of nitric acid. So 2 millimoles of nitric acid to 1 of sodium carbonate. The molarity here for sodium carbonate was 0.108 moles per liter. And we saw over here in the purple how we can just put millis into that and it's still the same relationship. So 0.108 millimoles per milliliter. And then at the end here where I've got milliliters of HNO3 per millimole of HNO3, that's the molarity over here. And I'm going to put, and leave enough room. Let's see. Just move that over. 0.150 millimoles for 1 milliliter of HNO3. I didn't have to calculate any molar masses because I used the concentrations and those were given to me. So 35.7 times 0.108 times 2 divided by 1.15. And thinking ahead, I should have 3 significant figures, 51.4, write down 2 extras, which is all there are, and round this to 51.4 milliliters. Anybody else get that value? If you go to the tutorial center and a tutor says to use M1V1 equals M2V2 for a chemical reaction, debating what I should say here, run screaming into the night, report them to the chemistry police, say, Mrs. K told me not to do that. Say, just refuse, because it's wrong, okay? What would be missing is this term in here where you have the 2-to-1 ratio. If this happens to be 1-to-1 or 2-to-2, then it works out, and that's why people keep doing it, but it's wrong, okay? Here we have different compounds. When we have a dilution, it's the same compound. Yeah?
Didn't we technically do the dilution equation and then just times it by 2?
That's a good question. Couldn't we just use the dilution equation, then multiply by 2? How do you know you're supposed to multiply by 2 and not divide by 2? Right? You'd have to really think about it, and it'd be easy to get that wrong. This is stoichiometry, which we have to learn anyway. And so when we follow this pattern here, the units put themselves in the right places and we don't have to think as much. So if you just embrace stoichiometry as a fact of being successful in chemistry, just get on board with it, it's actually easier because you'll get the right answer all the time and you don't have to think as much. Okay? It can be done. There are definitely other ways that you can solve this problem. I just don't recommend them because I've seen people just mess them up so badly.
How would you know to multiply or divide?
Well, that's the hard thing, right? You'd have to put the units in with the identification of what the compounds are, and then you're going to end up with moles of something and moles of something left, and you're going to have to apply this factor anyway. And yeah, it seems like it would be faster or easier, but actually it's not. It's one of those shortcuts that takes you all over the place, and then you get lost and have to go back and go the long way anyway.